All right, free response time for mechanics. So before we start, we just get some questions about how reflective my difficulty is of the real thing, because it doesn't really look like AP Classroom. So realize that a lot of the AP Classroom materials are there to show you kind of the extent of question we can ask. So if you look at the 2025 release test, it's a lot more straightforward than the stuff you see online. So you can assume that you're going to get usually pretty straightforward scenarios. We've stopped sort of creating these weird, cute scenarios that are just out there. We think it's better for assessing student understanding if we pick more typical things. So I would rank this on like the easy to medium side of questions I could create. I think this does a good job of covering most of the course content, which is why I put this in here. All right, so first we got our MR mathematical routines, which is basically simple math. We have a hollow sphere with mass m, radius r, and rotational inertia 2/3 mr squared. So we know this is going to be a rotating question. We send it at a speed VO towards this rough patch where the friction coefficient is mu. It's actually kinetic friction because we have slipping. And we're going to be interested in a couple things here. So when doing the MR, it's important to see what comes first. Is it symbol math first or is it picture? And here it's actually drawing forces. So if you have to draw a picture first, that means the point of the question is that the picture should help you with your derivation. Now, if it's the other way around, that means your derivation should help you draw some sort of a picture. All right, so we want to draw and label the forces exerted on the sphere while the sphere slips along the rough surface. So we're just drawing our forces. There's not too many points here, right? It's just 2 points for this diagram. So we can't really break the bank with anything. Well, first of all, the sphere exists on Earth. So we are, of course, going to have a gravitational force exerted at its center of mass, going straight down. I probably could do a better job of making that look actually like it goes down, and make it look like it's in the center, but got a gravitational force. And then it is in contact with the ground. So the ground exerts two forces, or two force components, I guess. One of the forces exerted by the surface we know as the normal force. So our normal force is going to go upwards at the point of contact. And then this is slipping, and it is moving to the right. So since the sphere is moving to the right, to oppose sliding or slipping here, our frictional force is going to point to the left. So how do you get your points here? Well, you get point A1 by drawing the gravitational force at the center, and you get point A2 by drawing the other two. So you have to draw Fn and kinetic friction at the bottom. Also, a lot of questions like how do I label these? It does not matter. If you label them any reasonable thing that you've seen in class, we know how to read them. So you could call this mg, you could call normal force n, you could call it just lowercase f. That might get a bit dicey, but we're pretty generous. If you use reasonable force labels, you do have to label them though. All right, now we have, after traveling along the rough surface, the sphere begins to roll without slipping. Drive an expression for the center of mass of the sphere once rolling begins. And it says, express your answer in terms of VO and physical constants. So it's important when we say express your answer that as of now, we're not actually going to tell you any like random symbols in this set that aren't in the answer. So it actually means the only thing is in terms of V0. So all of our other symbols should eventually cancel. Okay. So it makes sense that we're going to have a different speed because we're going to be slowing down due to this frictional force. But why do we begin to roll without slipping? Well, as soon as we see roll without slipping, we know somewhere in the derivation it's going to utilize this fact that if you're rolling without slipping, V of the center of mass is omega times r. So we're going to need to know V of the center of mass and omega, and we can set those equal and see when slipping stops. Because if we think about what's happening here, is there's two effects. So first, friction is going to slow down the disk translationally. But also, this friction force is causing a torque about the center of the disk. So the disk is going to speed up rotationally. And eventually, the speeding up of the rotation is going to match with a factor of r, that center of mass speed. And that's when we get rolling without slipping. So this is just about forces and torques. So we'll start just with the forces. So we know that the sum of the forces is going to be equal to ma. And I always just do sum of forces is like help minus hurt the motion of the sphere. So the sum of my forces, I have nothing helping the motion of my sphere, but I have the kinetic friction force fighting the motion of my sphere. Kinetic friction is always mu times normal force, and actually we just said it is mu, because this is kinetic friction. And we're on a flat surface with nothing strange happening, so our normal force is just going to balance the weight of the sphere, so we get mu mg is equal to ma, so our acceleration is minus mu times g. So we'll keep that in mind. That is going to be important for us later, because we can't just know the acceleration linearly, we also need to know the acceleration rotationally. So now we could also do this relationship that we know the sum of the torques is equal to I times alpha. Now, what is causing a torque? Well, we get to pick our pivot, and it makes sense to pick our pivot point to be the center, because that's where it's most easy to measure this rotation. We're looking at the rotation about the center of mass, so we should use center of mass here. So the only force that causes a torque is going to be friction, and that is a speeding up torque, because normal force, that has a lever arm of 0, and gravity is acting at the pivot point, so nothing there. Alrighty, so now we can just say the torque, which is Rf, so we have a frictional force at a distance r, causes a torque about the center. We have that rotational inertia, and we have alpha. And now we can solve, because we said that frictional force was just mu times normal force mg. So mu mg times r is equal to 2/3 mr squared times alpha. All right. You can do some canceling, and we get alpha is equal to 3/2 mu g over r. Right, because we bring the 2/3 to the other side, we cancel an m, we cancel one of the r's, and we know that our units should not totally match, right? Because we have a mu g for linear acceleration, and then we're dividing by another factor of r for the rotational. All right, that's acceleration for each of these. So why does that help? Well, notice this is a constant acceleration. So since these accelerations are constant, this means we can write the following. We can say that v, for the center of mass, we can just use kinematics. Right, we have a velocity function that's linear. So we have a velocity of v0, and we lose mu g units of that velocity every time unit. And then similarly, our angular acceleration is constant. So omega is equal to omega 0 plus alpha t. We have no initial angular velocity, so we can just multiply our acceleration by time. Now, all of this is to allow us to set these quantities equal using the no-slip condition. So VCM is equal to omega times r. So we get V0 minus mu gt is equal to 3/2 mu g over r times t times r. So that gets rid of that extra r we were dealing with. So we get V0 is equal to 5/2 mu gt. So t would be equal to 2/5 v0 over mu g. That's how long it takes before slipping stops. And then lastly, we just have a plug-in to do where we need to find the actual velocity of the center of mass. So we just substitute that value of t. Our acceleration was minus mu g. So we have v0, 2/5 v0 over mu g. Alrighty. So we get v0 minus 2/5 v0, which is nice and clean, 3/5 v0, which interestingly enough is like the coefficient for like the solid sphere. I'm not sure if that's a coincidence or not. All right, let's talk about scoring. All right, so you get 1 point for some sort of multi-step derivation using Newton's laws in both forms. So that would be, you'd get that sort of over here somewhere. So we'd say that's how you get A3. A3 is just multi-step. So you actually get 5 points here because this is not a scaffolded derivation. All 5 points are here. Now, you get a point. You get point A4 for the correct translational acceleration. You get point A5 for the correct angular acceleration. You get point A6 for applying the no-slip condition. And then you get point A7 for a correct answer. So you can see there's easy points and there's hard points. So even if you didn't know a lot, you could still get this point A6 if you recognize the no-slip condition. And I do believe I said that kinematics gets you one of these points. You can check my rubric. I think there's multiple ways of earning some of these points. This might not be like the law. I encourage you to look at my rubric. I spent a lot more time looking through the different solutions for that. So this is definitely like one of the harder questions because there's lots of different things combined here. And then we're not done. Now we do a little mini derivation. So again, the part B can just be totally on its own island. So we just totally change the scenario, but make it at least somewhat related. So we have the same sphere with same rotational inertia, and we put it at an angle theta with the horizontal on a plane. We release it from rest, and now we do roll without slipping. What is the static friction force on the sphere? Okay. We're allowed to use m and theta and g, right? That's a physical constant. Okay, so we're going down the plane here. So we know nothing about like the friction coefficient, right? Because static friction is variable. So a quick like wrong answer would be something like mu times mg cosine theta. First of all, we don't have mu. But second of all, this is the maximum permitted value of static friction, and we don't necessarily know that that's a thing. We don't know that it needs the maximum value here. So let's draw our forces. So since we're on a ramp, we do our modified free body, where we don't like to draw just mg. We don't like to draw just mg, unless if it's a free body that asks you. Like if you're actually problem solving, actually break the weight into components, where we have the down the ramp weight component, and we have the in the ramp weight component. And then to keep the block from just falling, or the ball, to keep it from falling into the ramp, we know that the normal force from the ramp must exactly cancel the into the ramp component. That's actually not relevant here, but there we go. So now we got to figure out what's going on with friction. Now there's two ways of figuring out the direction of friction. The first way would be to think about what would happen, what friction is to oppose sliding. Because remember, the bottom of this disk is stationary, or sphere, whatever. It's stationary. So if I were to release the disk from rest, it's going to slide down the incline this way. So to oppose the sliding down the incline, the frictional force must point up the incline. We can do a better job of pointing it along the incline. And this is static friction. So that's one way of figuring out static friction goes up the ramp, is to prevent this dot on the bottom of the sphere from sliding down the incline, which is what would happen if you release a non-rotating disc from rest. We point static friction up. Now, the other way of doing it would be saying, what is happening to the rotation of the sphere? Well, when the sphere reaches the bottom of the ramp, I know that when the sphere reaches the sort of bottom of the ramp, it's going to be moving this way. That's going to be its center of mass velocity. But I also know that it's going to be rotating that way. So I have to ask, who is causing the rotation? Well, it has to be friction. So what way does friction have to point to speed up the rotation in this clockwise direction? Well, the friction must be pointing up the ramp. So there's two ways to figure out friction is up the ramp. All right, now it's a similar scenario. I'm trying to decide if I want to show the sneaky parallel axis theorem solution or not. I think let's do that later. Okay, so we can just do net force and net torque once again. So and we'll just keep my notation consistent. So my net force acting on the sphere would be the mg sine theta that helps the motion minus the static friction that fights the motion. And we know that F net is equal to ma, so we get ma is equal to mg sine theta minus fs. That gives us an equation we can work with. Then we also know that the sum of the torques, and first I'll show the sort of traditional way where we're just going to sum the torques about the bottom. Nope, center, sorry. Is equal to the torques helping the motion, which is static friction, applying a torque at a distance r with the lever arm. And there's no torques fighting the rotation. And that's all we can do with this. We do know that this is equal to I times alpha. So we can actually do more with this than I initially led you to believe. Rotational inertia, 2/3 mr squared still, it says. And since we're not slipping, we can substitute A over R for alpha, because we can use the no slip condition that we know A equals alpha R. So we can just reverse that to get A. So if you actually simplify this down, we would get Fs is equal to 2/3 ma. It looks like, yeah. Yep, that makes sense to me. 2/3 ma. So we're not actually trying to solve for A, we're actually solving for the static friction force. So I might try to eliminate A from one of these equations. And since this is already solved, I think let's just solve for A would be equal to 3/2 Fs over m. That might be helpful. And I'll plug that in over here, because I get ma, where A is equal to 3/2 Fs over m is equal to mg sine theta minus Fs. So I would get 3/2 Fs equals mg sine theta minus Fs. So I'd get 5/2 Fs is equal to mg sine theta. So I would get Fs is equal to 2/5 mg sine theta. So there is our answer there. There is an alternate method that gets acceleration really quickly, and then you can just plug in acceleration over here. And maybe I'll scaffold that on the side, where you could actually do like You could do the sum of the torques about the bottom is equal to parallel axis theorem, moment of inertia times alpha, where you could look at the torque caused by the gravitational force. So you get this relationship that mg sine theta times r is equal to ICM was 2/3 plus mr squared. You get 5/3 mr squared times a over r, and you would get a is equal to 3/5 g sine theta. So you could actually do this sort of side method, and it's okay if, like, I just kind of walked through this quickly. Some people like being creative and picking your pivot point to be in like a cool spot. So if you actually just sum your torques at the bottom, you can get the acceleration, which is one equation, and you could plug that in. So let's talk about points here. There's only 3 points in B. I believe. Let's see. What did you have to do? I believe that, well, we know that this is B3. You have to have a correct answer. That's B3. To get B2, you had to somehow substitute, you had to do some sort of substituting for A or frictional force. You had to substitute one of these Newton's law equations into the other. And then for B1, you needed a multi-step derivation that involved Newton's laws 2 ways. You did have to get 2 ways for B. Although I think on the criteria list, you might also be able to earn the point by incorporating no slip. Again, check the rubric. But yeah, this is the hard one. This is the hard question because I blocked out 25 minutes for it, and I'm at about 25 minutes here. We'll see. I go way quicker through the rest of them, but this is pretty time consuming because there's a lot of math happening here. So yeah, this is showing that this free response set isn't entirely free. Like, you do need to know quite a few things to nail all the points here. All right, now we got a nice one. Now this also looks kind of scary because it's about rotation, but this one's not bad. We have a thin rod attached to the ceiling. It has a mass m distributed uniformly along its length L. The rod is pivoted about its top end, and we displace it a distance theta 0 before letting it go. Then a short time later, it's going to pass through. It's going to pass through the midpoints, and then it's going to continue swinging, and it stops sort of symmetrically on the other side. So what is this? Well, it's obviously a pendulum. So the TBR, this is not, even though it's the most points, this is usually not the hardest question. It just tests the most different skills. So the TBR, it actually makes sense to read all the parts first. Now that might be a good strategy for all the questions, but the TBR especially, because they're not usually like a sequence like you'd see in the MR. It's really like a series of things that exist at the same time. So figure A is a bar chart. It says UG equals 0 when the rod is at its lowest position. We just got to do kinetic and gravitational potential energy at the start, at the bottom of the swing, and at the other top of the swing. Then we want to derive but do not solve a differential equation that relates the theta, that relates theta to at least some of its derivatives. And actually, this is fixed on the paper version. I did actually need to tell you that the rotational inertia about the pivot point is 1/3 ml squared. That is derivable, but it's put in here. So if you're actually looking at my text version, I actually put that in there. I forgot to do that. Part C wants us to graph the angle, the pendulum angle as a function of time, and the angular velocity as a function of time for one cycle. And D asks, is our graph consistent with our bars? Okay, so lots of cool things here. I really like simple harmonic motion as a TBR topic because you can integrate bar charts and graphs and differential equations nicely. All right, this is really straightforward here. We're saying define UG equals 0 and the rod is in its lowest position. So we're defining UG equals 0 at this 1/4 t because the rod is in its lowest position. And then we're just going to draw our bars. Well, at t equals 0, the bar is not moving, so it does not have kinetic energy. Which means that all of our energy is budgeted in gravitational. Now, it doesn't matter how many bars you draw, right? You just have to be consistent throughout with some things. So if I had an energy budget of 3 bars that I put all in gravitational, well, when the bar is at the bottom of the swing and moving at maximum speed, I must have given my entire energy budget to kinetic energy. So I'm going to put all 3 bars in kinetic. And then we're just symmetric on the other side. So this is the maximum displacement, but on the other side. So it has stopped moving. It's at its maximum sort of height. So it's the other way. All right. It's actually not A1, A2, A3 for getting just each of the bar charts in sequence. I believe A1 you get by saying, we'll put this over the relevant bar chart. So to get A1, you had to say K was equal to 0 at this time, and you had to say UG was not equal to 0 at this time. And you had to say match with T over 2. So to get point A1, you had to have matching bar charts at 0 and T over 2. And you needed kinetic to be 0 and gravitational to be not 0. Then for A2, this bar and this portion entirely was A2. So to get A2, you just had to say kinetic was not equal to 0 and UG is equal to 0. And then to get A3, you could have totally wrong bar charts. You just had to show E total is constant. So as long as your bars add up, throughout this entire process, it works. So that's how you get your 3 bar chart points. So your first bar chart point you get just by having no kinetic but all gravitational at 0 and T over 2, making sure they perfectly match. You draw maximum kinetic and 0 potential at 1/4 T, and you get A3 just by making your total energy constant. All right. Oh boy, differential equation. Well, there's only 2 ways to get differential equations. It's, well, actually in this class it's just one. It's Newton's laws. You just have a choice of which Newton law. Well, this is theta, so we want to use torque once again. Okay. Now, there is like an alternate solution to this involving physical pendulum from the formula sheet. I'm not going to do that way. There's a way that like you can reverse engineer the period of a pendulum from the formula sheet to create the diff-EQ. That is definitely full credit if you manage to figure that out. All right, so I'm just going to draw my rod like that. It's actually bothering me that this is very not straight line. All right. We have our rod right here. So we are interested in this angle, theta. Okay, so what are the forces acting on this rod? Well, the only force that's acting on this rod that's creating a torque is gravity, right? We know that the gravitational force is going to act at the center of this rod, and it's going to point directly down. So the challenge here is figuring out things like, what is this actual torque? Because we know the force is just mg. So we know that we're just using the relationship. The sum of the torques about the top pivot is I times alpha. And we know that I is 1/3 ml squared about the top because I told you that, and that's alpha. All right, so how do we find the torque? Well, there's lots of ways to find torque. We know that torque can be found by R cross F, which is equal to r times f perpendicular, which is equal to r perpendicular times f. All of these are the same. Now, the cross product definition is kind of annoying, so I never use that one. So one way to do it is we could find the component of mg that's perpendicular to the distance of application and plug that in. The other way of doing it is finding the distance perpendicular to the line of action of force. And that's actually going to be the lever arm approach that we're going to use today, because we actually will know the distance, that distance, because it's horizontal. Because anytime you have vertical or horizontal forces, you want to use lever arm with torque, because it's really easy to track. So what I mean by that is that our lever arm is going to be this distance right here. I extended it a little bit too far. It's going to be this distance. Because what lever arm is defined as is it's the distance you have to go perpendicular to the direction that the force acts. So if the force acts vertical, your lever arm is horizontal. If your force is horizontal, your lever arm is vertical, and so on. So all we have to do is figure out whatever this green length is. So let's do that. I think I'm going to make my picture a bit larger here. All right, so this angle was theta. And we know that if gravity acts at the middle of the rod, we know that this length right here is going to be L divided by 2. So if we want the distance from our pivot point horizontally to there, we can also just say this is our lever arm. Our lever arm will be this green distance right here. And this is just going to be L over 2 times sine theta. And it's sine because the lever arm does not touch theta right here. So we can just go in and do that. So our torque, all of that to say, our torque is just r perpendicular, which is L over 2 sine theta, times F, which is mg, equals mg 1/3 mgl squared alpha. Nope. 1/3 ml squared alpha. There we go. All right, we can do some simplifying. This is not yet a differential equation, so at some point we're going to make it differential. But we can get, solving for alpha is going to be equal to, oh, and this is a restoring torque, so we can make this negative, although I didn't demand that in the solution. 3/2 g over L sine theta. And what I mean by restoring torque is I made this torque negative because what the torque is doing is the torque is not going to make theta increase. The torque is actually decreasing theta at this time, right? It's a restoring torque. It always tries to send the pendulum back to equilibrium. So I put that negative there, although I did not grade for that. I didn't think that was necessarily the most fair thing to grade in this. All right, so this is almost done. Now there's a couple things we can do. So it actually does say assume the small angle approximation is valid, because that's going to help us create a graph later. I didn't force you to use that. We could also, but since the small angle approximation is valid, we're going to just take this, shrink it down a bit, get it out of the way, using the power of editing software. Small angle tells us that sine theta is approximately equal to theta. So I could actually approximate my differential equation as 3/2 g over L times theta. But it's not a differential equation yet. We have to relate alpha and theta using a derivative relationship. Well, we know that acceleration is the derivative of velocity, but velocity is the derivative of position. So we're just taking two derivatives with respect to time of theta. So this is the rubric answer. We can accept things without the minus sign. You don't have to get rid of sine if you don't want. We accepted that as well. This is the intended answer. Let's go through points. All right, you got a point for Newton's second law for like the third time today. That's B1. You got point B2 for the correct torque. So for somehow getting the correct torque side of the equation, we got that. To get point B3, you had to do the small angle approximation, or you had to recognize d theta dt. So to get B3, you had to say sine theta is approximately theta, or you had to make the substitution alpha equals d squared theta dt squared anywhere. And to get B4, you just had to get the correct answer. So there's your points there. 2 of the 4 are probably easier than the others. Now we got the graph, which actually is not super difficult. So the point of this with the small angle approximation is knowing that this will be simple harmonic. So we want the angular displacement, and it says defining the displacement to be positive at t equals 0. So notice we have our angle that sort of is maximized. Then a quarter cycle later, the rod is swung into the vertical position, so theta is 0. Then a quarter cycle later, it's going to reach its maximum value, but in the other direction. Then it will swing back in the middle, and then it reaches its initial position once again. And we know that this will be sinusoidal. All right, that's actually not terrible. And then omega, we can do by thinking about the speed of the rod. So if I release the rod from rest, it's not moving. Then when it goes to the center, it is going to be moving with maximum angular speed. And it's actually moving in the direction of sort of negative theta, because our angle is decreasing at that moment in time. So it's there. And we know it's just going to make a trig function. All right, not my worst graph ever. So there's another way you could do this if you didn't want to think about it using like the actual speed of the bar. We also know that this comes up in the rubric. We also know that omega is just the time derivative of theta. So you could also have done this just by looking at the derivative. So my slope is negative at the start. Then it's maximum negative value at quarter cycle. Then it is flat at 2/4. Then it is maximum positive value at 3/4. And then the slope is flat again at 4/4. So how'd you get points here? Well, your first point, to get C1, you needed let's see, what do I have here? That's a remember, sorry. I know what C3 is. I know that C3 is omega has to be the derivative of your theta graph. C1, I believe that C1 just had to be theta is given by like a positive cosine function, and omega had to be given by a negative sine function with one cycle. This is definitely my least refined aspect, is like remembering the rubric points off the top of my head. But basically, getting the theta graph correct got you C1, getting the omega graph correct got you C2. To get C3, you had to have this sort of derivative relationship where it must be reasonable that your omega could be a derivative of your theta, where you just look for the slope, the points of zero slope lining up. Alrighty. Now we get a little break here. Indicate whether our graph of omega versus t is consistent with the bars. Well, what does consistent mean? Consistent doesn't mean match, because it doesn't have to match. In this case, it actually will. But so what would it mean to be consistent? Well, the bars in part A are about energy. And more specifically, if we're talking about angular speed, that should relate to kinetic energy. So we know that rotational kinetic energy is 1/2 I omega squared. So to check if they're consistent, the energy bars should be maximized for kinetic when omega is maximized. So omega is maximized in absolute value at 1/4 and 3/4. Now we didn't draw bars for 3/4, but we did draw a bar for 1/4, and notice that is where kinetic energy is maximized. So it is consistent. So since kinetic energy is proportional to omega squared, the kinetic energy of the bar and kinetic energy of the bar and the angular speed of the bar are maximized at the same times. So this actually doesn't earn full credit. You have to say consistent. So just, I usually like to lead with consistent, but this is more like building a coherent argument. So how did you get these points? Well, actually realize that with the new physics C's, we don't really grade for justifications. We're really grading for like physics facts. So this is a lovely argument about the bar being the kinetic energy and the angular speed have to be maximized or minimized at the same times. All we were looking for is this. Now, it did say referencing functional dependence. You shouldn't say they have to line up. You have to specifically say this relationship or this proportionality. You have to say kinetic energy is proportional not to omega, but to omega squared. So we needed that. So correctly identifying consistency gets you D1, and omega squared relationship gets you D2. So even you can even get the consistency point if it wasn't consistent, as long as you say so. To get D2, you just have to say this fact. So it is possible to earn D2 without D1. All right, those are long two. Now we're just going to do the lab question and the QQT. So the lab question is just kind of garbage, just plug and chug. All right, experiment 1. Students are asked to determine, gee, what a surprise. They have this adjustable stand. They have a sphere that they can release from rest at different heights. They can adjust the height using a stand, and the students have a stopwatch. So this means we have access to measuring h, and we have access to measuring t. The goal of this is that you should be like really forced into a box where you're given these two things you can use to measure. Indicate quantities that can be measured. This is not procedure. We've gotten rid of this being a procedure question. This is literally what can you measure? So what can you measure? We can measure the height, we'll say the fall height, h, and we can measure the fall time, t. That's how you get A1. You just have to say measure h and t. How do you reduce uncertainty? Well, of course, we repeat for multiple values of h. Any reasonable thing like repetition or any error thing works. Repetition of trials is the easiest one. So again, people think that this is really a physics question. This is not. These questions assess science skills. So that's why a lot of these points are cookie cutter and easy. We're not actually trying to assess your physics with most of this question. It's about science practices. All right, now here's where some of the physics points show up. What quantities can be graphed to find g? Well, this is just a sphere in free fall. So since the sphere is in free fall, we can use kinematics. Now, if you're trying to be all formal, you can start from start from this. But of course, I hope at this point, if you've done free fall enough, you know that you can get this relationship that says h equals 1/2 gt squared. Right? Because our acceleration would be g down, and we travel a distance h from no initial velocity. So that means that if we're graphing this, we measure data for h and t. So I can put h in a box, and I can put 1/2 g in front of t squared. So we can graph h versus t squared. Anything equivalent to that works. You can transform this however you'd like. If you want to put 1/2 in the box, you can do that. If you want to multiply 1/2 to the other side and put it in the h box, you can do that. All that stuff works. Now, you can't, well, actually, no, that's fine. It's fine for B1. Make sure that you say what is going on what axis. Versus is good. And is not. Don't say h and t, because that's confusing. Now, I'll show you like my way that I always do it that is extremely clear and gets you the B1 and B2 in just one line. Is you would say, well, we said we're graphing h on the y-axis and t squared on the x. Here's how you get all your points guaranteed. You don't need to solve. A lot of people think you got to do algebra on this. You don't actually have to. We test that in C and D. So h, that goes on our y-axis. T squared, that goes on our x-axis. 1/2 g is our slope. Boom. Those are my points. That's how I get B2. I just said that is my slope, 1/2 g. I actually graded the mechanics lab question last year. I loved the responses that just did this. It's so easy to see that you graphed everything, that you know what you're graphing if you indicate it like that. There's no ambiguity at all. Now, if I wrote this in words, my rubric says graph h versus t squared, slope is 1/2 g. You do not need to solve for g. You just need to relate g to the slope somehow. So you don't have to do any sort of algebra, because any sort of solving will be found in CD. All right, in experiment 2, the students are asked to use a linear graph to determine the magnitude F of a constant force exerted on a pullback car accelerating from rest along a frictionless surface. The students add various masses to the cart and record the mass m of the system. They pull back the cart a set distance, and they record the speed v after the car has been traveling for 2 seconds. So we are just letting the car experience a force for 2 seconds for different masses. Now, there's a couple of ways to derive an equation for this. We are trying to find F. Now, my original intention for this problem is, for mechanics, we try to make like a rotation question, energy conservation or momentum conservation, forces, and something else. Like we try to do momentum, forces, energy, rotation, something like that. Now, here I actually thought about momentum first as like how you get the equation, because we're applying a force for a set time. So I actually intended for you to do this by saying impulse momentum theorem, F delta t equals m delta v. And we start from rest, so you just get F delta t is equal to mv. That's one way of coming up with this equation. Now, another way of coming up with this equation, where our variables, just as a reminder, we were given m and v. So we're going to have to do some manipulating, because delta t was just 2. So another way you could do this is you could just say F equals ma. So acceleration is equal to, actually we can just substitute here, where acceleration is just delta v over delta t. So you would get F is equal to m delta v over delta t, or our expected result, F delta t equals m delta v. So that's 2 ways of getting that. Now, this isn't linearizable yet because we have just a bunch of stuff on the right side. So you have to separate your lab variables to get a linearization. Now, since v was kind of on my y-axis originally, I'm just going to divide everybody by m. So I'm going to do that here. So we said that f delta t is equal to mv. So I could solve for v, and I'd get v is equal to f delta t over m. And it's always good practice just to separate your variable from the constants. So f delta t is a variable, or sorry, is a constant. So I'm going to separate that 1 over m out from there. And now it's going to be clear to me what my sort of boxes should be, because I have the relationship v equals f delta t times 1 over m. So I can put v in a box, I can put 1 over m in a box, and then that means that my accelerator or my slope is f delta t. Now, if you want to just call delta t 2 at this point, you're totally fine to do that. Like, we don't, this is more just about getting the correct answer. So if you graph v versus 1 over m, the slope will be f delta t. All right. Magic, video, editing, mining off camera, whatever you want. Here's the graph. So here's how you get all your graph points every time. So C1, if you don't know physics, if you don't know the physics of the problem, you're not going to get C1. So C1 is for your linearization. So meaning you had to have picked a linear quantity. So I can't just graph random garbage and get C1. I had to graph something that makes a straight line. So V versus 1 over M is straight, so that counts. C2, C3, C4 are always free. Just commit to graphing whatever wrong relationship you came up with. If you know it's wrong, you'll get these 3 points no matter what. C2 is for axes with a linear scale with units. Now, if you graph strange stuff in your boxes, it's going to be hard to get the units right, but just try it. So I get it by saying V is in meters per second, 1 over m is in inverse kilograms, and then I had to scale my graph linearly. A linear scale needs at least like 3 ticks to show that the spacing is consistent. All right, now for C3, you just got to plot the points. Very few people lost this. Like, very few people did not earn C3 on the questions I graded. And then C4, you get your best fit line or curve if you know it's not linear. So just a reasonable best fit line. All right, so I just Desmos this to get my best fit. And our relationship on the other page said that the slope was equal to f delta t. So 1.69 was equal to f times delta t, which was 2. So my force F was 1.69 divided by 2, which is 0.85 newtons, roughly. So to get D1, you had to like write an equation with slope in it somewhere. You just had to say like the slope relates to F this way. It did have to be correct. And then D2, you had to have a correct force value. So anything that was like close to this, you can see exactly what I decided the range was. But if you did correct physics and had a correct best fit line, you're probably in the right range for F. So that wasn't bad. That wasn't bad. All right, last we got the QQT, where we are sending a block at 2 different inclines. We have a shallow incline, and then we have a sharp incline. And for A, we want to consider the moment in time when both blocks have traveled the same distance d parallel to the incline. So that means we've gone the same sort of slant distance. Compare the absolute value of the work done by friction on the block. Okay, well, let's think about this. So I always like to just do my justifying and then I check the box. Unless if the question is super difficult, I'll actually do part B first, and that'll inform me like what the answer should be. And B says derive an expression for the height reached by the block, so that actually doesn't look helpful. Okay. All right, so we want work done by friction. So what is work done? Well, work is just going to be the frictional force times the distance d. right? Work is force times distance. And we are given they're traveling the same distance d. So distance d is the same. Okay, so that at least gets us to start. So really, we're not comparing the work done anymore because we know work is just force times distance. So we know that since the distance is the same, we're really just comparing the frictional force. So what is frictional force? Well, frictional force is just equal to mu times normal force. So what is normal force? Well, again, the normal force is the force component that sort of points out of the ramp. So we have to think about how that is going to compare for each of these ramps. So for this ramp, my flatter one, my normal force is going to point out of the ramp like this. And then for my other scenario, we just have to think about how gravity is going to sort of split, might be a better way of thinking about it. Because normal cancels that sort of into the ramp component. So we know that there's going to be a weight component that pulls down the ramp, and then there's a weight component that pulls into the ramp. And then for scenario 2, it's the same thing. Oh, this is a very comically steep ramp that I drew here. Then for scenario 2, we see that we're going to have much more of the weight is sort of directed down the ramp versus in. So that actually tells us that since the ramp is flatter in scenario 1, we're sort of giving more of our weight into the ramp component. So we actually have a larger normal force for scenario 1. Because think about the extremes. If you have a totally flat ramp, your normal force is mg. That's the biggest the normal force could possibly be. If you have the extreme of scenario 2, that is a completely vertical ramp where you're not touching at all, so normal force is 0. So what this means is that Fn is larger in scenario 1. So what this means is that work is larger for scenario 1. Because we have the larger normal force over the same distance. Okay, how'd you get your points here? Well, checkbox gets you a point. So that's A1. You get a point for saying work done is force times distance and distance is the same. So these two lines combined get you A2. You did have to say distance is the same because that is important for comparing here. And then you also had to say that normal force is greater in scenario 1. So if you said normal force is larger in scenario 1, you do get that point. So we're just looking for these lines, right? It doesn't have to really be the arguments. We're grading the physics facts that you're citing. So I thought this was kind of a tricky justification. Derive an expression for the maximum height h1 above the bottom of the ramp reached by the block in scenario 1. Well, we got maximum height, so we got to be doing some energy conservation, right? So we're just going to set the kinetic energy at the bottom of the ramp. Well, actually, I think we'll draw it out sort of with a bar chart here to show what our equation will be. So at the bottom of the ramp, and then we have the top of the ramp. All right, so at the bottom of the ramp, we know everybody is going to be kinetic, right? And then at the top of the ramp, in a world without friction, we would get all of our energy perfectly converted to gravitational potential. Well, that's not what happens, right? That's not what happens. At the top of the ramp, we're going to get some of our energy has been converted to gravitational, but some energy was just dissipated by friction in the form of heat. So our energy conservation equation is going to look something like this. Of course, if you do different signs than me, like if you just know that the work done by friction is negative, you can put that on the other side. But I'm getting something that looks like this as my energy equation if I call the work done positive. I'm just doing like the actual like energy bars here. So this is how I write my equation. So kinetic energy at the start is 1/2 mv squared. Gravitational potential energy is just mgh. And then we said the work done by friction is just going to be the frictional force times the distance it travels up the incline, which is not h, right? Because friction is going to act along this incline. So we actually have to do some trig to deal with our slant height there. All right, so now we'll do some substituting. So frictional force is mu times normal force. And normal force is mg cosine theta on a ramp. That's just on my memorized list, right? You should just know that mg sine theta pulls down, mg cos theta pulls in. So this would tell you that v squared over 2 equals gh plus mu gd cosine theta. Now we're solving for h, and we also have this thing d in here, so we have to do some trigonometry real quick. Where we're going up this ramp, this angle is theta, this distance is d, this distance is h, and we're interested in eliminating d. So we know that h would just be equal to d times sine theta, because it's the vertical component. So d is h divided by sine theta. So we can just plug in. So you get v squared over 2 equals gh plus mu g h divided by sine theta times cosine theta. So something interesting is going to happen with trig functions there. So we get v squared over 2 equals gh plus mu gh. Cosine divided by sine is cotangent. So we get v squared over 2 equals gh times the quantity 1 plus mu cotangent theta. So this tells us that the height h1 reached by the block would be v squared over 2g times the quantity 1 plus mu cotangent theta. Oh, how lovely. How lovely indeed. Yeah, maybe this set is harder than I thought it was. I don't know. That's kind of up for you to decide. So maybe it should be bumped to just solid medium. How did you get points here? You got points for a multi-step derivation using energy or Newton's laws. I was kind of Newton's laws outed. I was kind of just done with Newton's laws at this point. My rubric shows you how to get all the points if you use kinematics and stuff. So you got B1 by just doing a multi-step derivation. You get B2 by like a valid conservation of energy equation. So like it had to have some stuff plugged into it that was right. And then all that algebra gets you B3. Now, if you did Newton's laws, you got a point for using Newton's laws. You got a point for the acceleration, I think, and then you got the answer point. All right, suppose instead of a block, we have a disc that is shot at the same speed up the same incline. Does the center of mass reach a higher height, a lower height, or the same height? I have counted like 4 ways you can justify this. So this was my intended solution, by the way. So we have a disk that's rolling without slipping. Here's my intended solution. My intended solution said the rolling disk also has rotational kinetic energy. Thus, since E total is higher, the maximum height it can reach is also higher. So this was my like intended solution. This was what I thought most people would gravitate to, saying it reaches a taller height because you just have more kinetic energy. That is one like justification. So to get C2, you had to say one of these like 4 facts. One, you could say the rotational kinetic energy sort of adds to the energy budget. That's one. For solution two, you could say that now it is the frictional force actually points up the incline instead of down the incline, which going off of that tells you the net force or net or acceleration is going to be lower. So it's going to be slowing down at a lower rate. Or you could say, well, now there's a frictional force acting on the disk, but it's static friction, and static friction does no work. So there's no sort of energy loss due to friction like we have in this bar chart up here. So there's like 4 ways of justifying it, which I think makes this a nice item at the end here. Alrighty. At some point, I'll update my scoring worksheet as like what I think the projected cuts will be when I have a large enough sample take this, whose performance I think is reliable. But yeah, overall, I think this is a good set for testing skills. Like it does put a lot of stuff in here. It's a bit light in terms of momentum or angular momentum. That's kind of the 2 big gaps on here. So I tried to fill those with a multiple choice. But I liked this set. I thought this was a good set of FRQs. It shows you the types of stuff we ask. So hopefully you found this helpful.